Hello, everybody. My name is Nima, and I, alongside Ayush and Jinwoo, will be presenting the paper Attention is All You Need. This is a paper by Google Brain and Google Research, where they introduce, as the professor mentioned, the transformer model for natural language tasks. So let's get started. So for general natural language processing, well, the what this paper does is it introduces a general natural language processing sort of model, but specifically in this paper they use it for a machine translation task. In this space, generally what we see is an encoder decoder architecture as seen in the figure, and the generally encoder decoder architectures are such that they take the input sort of the input text or the input vectors, and they encode that into a vector which contains the hidden state representation of that, and the decoder takes that hidden state representation and generates some desired output. So you can think about if you're trying to translate something from English to German, then you can take the input in English, then output some sort of hidden state representation, and then for the decoder stage, take that hidden state representation and output the German text. So for the prior state of the art, prior to this paper, has generally been revolving around the recurrent neural network architecture and sort of extensions on top of it, such as LSTMs and GRUs. And however, one thing that has been seen, as with the previous paper and with other papers that are cited within the Attention is All You Need paper, is that attention mechanism has been used sort of successfully to increase the accuracy of RNN models, and you can see a list of papers that sort of explore this topic. Now, one thing that we see generally with RNNs is they have a performance bottleneck because the training has to be done in a sequential way, and so what the transformer does is it completely gets rid of recurrence and it only relies on the attention mechanism. This allows the transformer to be much more parallelizable, and in their case, they mentioned that they achieve a new state of the art in machine translation after being trained for only 12 hours on, in this case, 8 P100 GPUs. Now, one thing that you'll see us sort of doing in this paper as we explain the architecture is, we'll be kind of referring to this paper as a general sort of NLP paper that could be used for multiple different tasks. Again, in the results, we'll see one of the main ones that we'll be focusing on is machine translation, but it can be applied for other tasks as well. So the transformer here in this picture shows the general architecture of the transformer. What we see is we have an encoder step and we have a decoder sort of step that are connected together. The inputs, you take in the input text, you create an input embedding from it, you add what's called a positional encoding on top of that. Ayush is going to go into more detail about this, and then it gets fed into a stack of n identical layers, and these layers are, again, you see it in the encoder stage, so it's a multi-headed attention, which is then fed into a normalization step, with the caveat that you have a residual connection that is added to the output of the multi-headed attention before the normalization, and then the output of that is fed into a regular feed-forward layer. And in the decoder step, it's exactly the same, but the output of the encoder is actually fed into the query and the key values for the decoder, and the value comes from the output of just adding another multi-headed attention and a normalization step. In this case, it is masked. And again, we'll go into more details about this. So the last thing I'm going to sort of talk about here is just the concept of self-attention. And so we can sort of think about self-attention as, if you have some sort of an embedding coming in for a sentence, you first tokenize those and you turn those into vectors, and then you can almost think about attention as a black box that takes that input embedding and outputs some other sort of representation that has context built into it. And the previous paper, they talked a lot about context. And so in this case, Bank of the River, being able to tell that we're talking about, again, a river bank rather than the Wells Fargo bank, that is where context comes in. And you need to pay attention to the word bank and river. Those two are connected to each other. And so we can think about attention as a black box sort of that does this. I'll be explaining what goes on in that black box. So what I want to do here is I want to first think about let's take a perfect world where we have a perfect representation of text into a latent space. So let's just say that we have a perfectly semantic latent space vector representation of words, such that if two words are close to each other, then they're semantically similar. Then you can think about the dot product operation as an operation that will return a very high value if two vectors or two words are close to each other in meaning, and it will return a low value if they are not close to each other. So when you think about this bank of the river, where every word turns into v1, v2, v2, v3, and v4, that goes in as into a sort of dot product module where, let's say in this case, we're processing the word the, which is v3, that gets dot producted with every single input. And what we get as a response or as a result is these S31, S32, S34, or so on. These are sort of the dot product outputs. Once we normalize those, what we get is a value between 0 and 1 of how similar those two words are. Now for the word v3, what we can now do is we can multiply these normalized values, the w3 ones, with each word that those correspond to, and add everything together. And this y3, again, assuming we have this perfect representation of words, is actually going to be a version of v3 that now has context built into it. Now, obviously, we don't have this perfect representation of words, so now we're going to talk about actually adding in the weights. And again, I'm going to go back to the previous slide and go to this one to show the difference, which is all we're adding now is to each one of these inputs, we're adding a matrix that is being multiplied. This is called the key. The sort of the combination of the vector and the matrix is usually called the key. The query, or which is the word that we're kind of interested in getting the more sort of a context representation of it, that is called the query, and that gets multiplied by a matrix. And then same thing at the end of the step when we're adding everything together, prior to that being multiplied by a value matrix. And the point is that these three matrices can now be trained basically, and you can now put these into your network and figure out the best best values for these. So that's effectively what we get in the paper. Now, what they add is there's a masking step. Again, this is used for in the training step. I'm going to skip it in this case, but for normalization, they use softmax, and they use a scaling operation prior to doing any of this. This is to make sure that the values don't blow up by a ton, so that when they do the gradients, the calculations can actually be done pretty effectively. And so that this ends up being the full sort of equation that we use for this. What's interesting about the self-attention module is that it could be repeated multiple times, and that's where that stack sort of concept comes in. So now this is an example. So on the right, in both of these, you see the word, which would be the query value, and then what you see here is kind of what that query and key matrix representation would give you, which is what word is it sort of connected to, or what is it paying attention to when we're actually going through the model. In this case, we're saying the animal didn't cross the street because it was too tired. So in this case, the it is an animal, so it's paying the most attention to animal. And in the second case, it says it didn't cross the street because it was too wide, so we're talking about the street, and we see the major connection that goes to the street. So this is a basic idea of what self-attention does. I'm now going to pass it along to Ayush, who's going to talk about multi-headed attention.
Yeah. Can you guys see my screen?
Yes.
Okay, cool. Yeah. So hi everyone. Yeah, so Nima explained how self-attention works. Now let's look what transformer uses and how does it fit in its architecture. So the transformer model uses multi-head attention, which is basically a parallelized version of self-attention. So what I mean by that is we have these queries, key and values. So what we do is we project them into different spaces, and in those spaces we individually do self-attention. After that we concatenate them and we do a linear layer. So that would give us the multi-head self-attention done on these query, key and value pairs. So in form of equation, you can see that the input is Q, K and V, and for ith head we transform them into some different space and then do attention, and after that concatenate them, and then we have a W projection that projects them back into the initial space. So yeah, and yeah, and in the architecture, the number of parallel heads for multi-head attention is that they have used is 8, and the dimension space for key and value is same, which is kept to 64, and the dimension for the dimension feature dimension for the model is kept to 512. So yeah, so I mean, so this is a small example. Let's look how multi-head attention works in terms of tensors. So let's say our input is just consisting of two words, thinking and machines. So yeah, and we can obviously embed them into word vectors. So if we are looking at the first input to the transformer model, then these X would represent the word vectors of thinking and machines. But if we are looking at some intermediate input to some encoder layer, then this would be R, which would be output from the previous encoder or previous decoder in whatever stack we are in. So yeah, so in the transformer paper, they split that into 8 heads. So we would have 8 different weight matrices for query, key, and value, and so that they could transform them into different spaces. So we have these Q0, Q1 up to Q7, same for keys and values. And after that, we perform self-attention between them. And this would give us a Z0 to Z7 uh, representation. Then we would concatenate them and transform them back to the initial space using this WO matrix. So this would give us the output Z, which is the output for this multi-head attention block. And this would happen on and on in different layers in the encoder. So yeah, now let us look at some visualization of multi-head attention. So in this, you can see that, I mean, if we look at the attention weights for it, you can see that in two different attention heads, the weight for it is quite focused towards an animal in one space, and in another space you can see that it is paying attention to tired. So in a sense, it means that the representation of it kind of consists of the in animal in one space, and the representation of it in some other space consists entirely based on tired. Yeah, and now let us see how attention has been used in this paper. So yeah, they have used it in 3 different forms. So first is just what I had explained, that is the multi-head attention, where the key, value, and query pairs come based on the representation that they have got from the previous layer, and then they do multi-head attention on based on that. So yeah, this has been done in the encoder stack and in the decoder stacks as well. And the second way they used attention is in the encoder decoder attention, in which is done inside the decoder block, in which they have query coming from the previous decoder output, but key and value coming from the encoder's last layer's output. So in this the output from the encoder is interleaving with the output from the previous decoder state, so that they could mix information here. So that this is the only point of interaction that happens between the encoder's output and the decoder. Yeah, and the third way they used multi-head attention is that they do some masking in the decoder state. So let us look what they do with that. So yeah, so if you look at this example, so this obviously the operations in transformers obviously happens in parallel. So for the input, if you would send in the entire sentence, it would give you the representation for all different words at the same time. But for the decoding step, during training, since we have access to ground truth labels, we can send the entire sentence, and we can process that. But what would happen is, let's say if you're looking at the first input, so during self-attention, it can have access to the future tokens that the model would predict and would get input to the model. So we don't want that. Otherwise, I mean, the model would just pay attention to the next token and take it and predict it trivially without using any reasoning or any self-attention. So in order to prevent that, what we do is during the self-attention step, just before softmax, we would set this value to minus infinity so that when we take softmax, this value goes to 0. And that way the value of v does not get added to the weighted context that we take during self-attention. Yeah, and now let's look at some another block. I mean, so after self-attention, there is this add and non block, which is essentially, I mean, they add residual connections from before they do self-attention to after when they do self-attention. So they add that, and this is x plus z, and after that they do layer norm, and layer norm is simply doing normalizing over the dimension in each instance. Yeah, and then we look at the feed-forward network that they have after add and norm, which is essentially a linear layer, two linear layers attached. So yeah, and in the input and the output of this is of dimension 512, and the inner layer's dimension is 2048. Yeah, and after that, let's look at these embeddings in the softmax. So in the transformer model, the input embedding, output embedding, and the final layer share the same weights, and they are learned. So I mean, this had been shown in some previous paper that the output embeddings for a neural network is usually quite similar to, I mean, for a language modeling task, it is quite similar to what they have for the input embedding. And if they try to, I mean, share these weights, I mean, it provides some regularization and it helps in performance as well. So they kind of took this idea from there. And yeah, and so in transformers, I mean, there is no recurrence or any convolutions, and they obviously want to add information about the positions of the tokens that they are using. So for that, they add encoding about the position using some vectors, which we'll look into. And yeah, and what they do is they keep the dimension of the position embedding same as the word embedding, so that they can simply add them and get a embedding with time signal thing. So yeah, so in this paper, they use this formula to get their positional encodings. So here position refers to the position of the token in the sentence, and I represents the dimension that we are trying to, I mean the dimension of the vector that we are trying to get. So you can see that at even places they get a sign of this formula, and at odd positions they get a cos of this formula. And yeah, and this is just a visualization of 10 token positions and where they have embedding dimension of size 64. Yeah, and now Jinwoo will explain why we use self-attention and the results.
Can you see my screen?
Yeah.
Yeah, let me take over the presentation from here, represent how the self-attention model works, then why is it important? First of all, because it requires lots of time when we train the large data set, we need to parallelize it. The researchers compares the result in a total computational complexity per layer and the minimum number of sequential operations. The second reason is that in RNN, the first data fade away as the training step goes, and this requires the research team to consider the path lengths to develop the model. Paper 1 summarized the comparison between the transformer model and the others. RNN requires less complexity per layer, but it also requires a sequential operation, ON. On the other hand, CNN can be computed in a parallel way in some sense, but in order to encode the long range dependency, it requires lots of computation for the complexity per layer because the K is in here and here too. In terms of the training, they use WMT 2014 English-German, English-French dataset. They use 8 NVIDIA P100 GPUs. Training times take 12 hours for the base model and 3.5 days for the big model. They also use ADAM optimizer with respect to the warm-up state. They use residue dropout and Ravel smoothing for the regularization. This is the result for the machine translation. We can see that transformer achieves the state-of-the-art result. And the efficiency also increases since the computational cost of the transformer is 1/100th of the other models. As you can see, the log scale of the flops number. And this is the result of the model variation and BLEU score. BLEU score is like, as you can see here, bilingual evaluation understudy. They change the number of heads, number of keys, and the dimension of each layer, running rate, and big models. They can check the importance of each factors. If they decrease the number of keys, the model's accuracy decreases as well. If they increase the number of each layer, the model's accuracy can increase, but also require lots of parameter. It takes lots of time to training, and also dropout decrease the overfitting. Like we can see from step by step here. And table 4 shows that the transformer can generalize to other tasks. The output is subject to strong structural constraint and is significantly longer than the input. The transformer outperformed other previous model except the RNN grammar model, which is like number 8. Then let's think about the weakness of this paper. I think they didn't include the analysis for each head in the multi-head concept. If they analyze each head's behavior, we can use the head more efficiently. And attention can only deal with the fixed length text string. So if the fixed length is smaller than the whole context, it loses the information. So it could be like better if it could be also the weakness of the like transformer idea. And these are the references that we use for the presentation. And thank you for listening.
Okay, so very good presentation. I especially like the animation of the self-attention part. Also, I see in the chat quite a few students think that part is very, very good. So let's give them a round of applause for the great presentation. So we have quite a few questions in the chat box, so let's look at them. So the first question is from Hart. So Hart asks, could you explain again in the slides without key and query weights why you said, let's assume we have perfect latent reputation. So I don't quite understand how the key and the query weights are learned. So could you explain what are the key and the query weights in that slides?
Yes, so I can share my screen just to bring up the slides again. So when I brought up the idea of having a perfect latent representation, I wanted to sort of motivate the idea of using a dot product to find sort of similar words or for example, if you think about the word bank, it could have multiple different meanings, but once you if you think of the multiple meanings as a linear combination of all the different meanings, then the dot product would still be high if you do that with river or something like that. So the point was that so the introduction of the perfect latent space representation was to just motivate why the dot product works in this case. Now, what we actually get as an input, let's say if you're in the first layer, assuming you have no positional encoding, is you end up actually getting words that are sort of the vector representations of each word within the sentence, and that might be quite arbitrary. It might just be the index of the word or the some sort of a way. So what you have to do is find some sort of a some sort of a linear transformation to turn the the representation that you have for your words, your input sort of word embedding, into a more semantic embedding such that the dot product actually behaves as it would in the case of the latent space representation. So that's the motivation of why you have these query, key, and value. Now, in terms of how they are learned, they would be learned within whatever task you are using to train. So if you're doing translation, this would be sort of like an end-to-end process, and just like any other sort of training mechanism, you're trying to decrease a cost function, and so whatever the value is decreased that cost function, those would be the values you would have for these weight matrices.
Thank you.
Okay. So what are the MQs and MKs? Are they corresponding to the Q and the K in the original paper in this slide?
Yes, and although in the original paper they're sort of generalizing, so in this case I'm talking about the first layer. They in the previous paper or in the sort of next slide, this Q, K, and V, they're generalizing so that you can have multiple sort of stacked self-attention modules. But in this case, yes, this is technically when you take the input and you multiply times the weight, that would be the Q, K, and V, sort of the combination of those two.
Okay.
That's what, yeah.
So, okay, let's look at the questions related to this first. Yeah,
Sorry.
go ahead.
And the input embeddings are just like pre-trained embeddings for each word, or is it?
No, they could just be. You could almost think of your entire data set where you have some sort of a dictionary of, let's say, 10,000 words, and each word within that has an index. So it would be a vector of that. And the point is, like, this is what you use to actually generate that. What for example, in BERT, what would be the pre-trained embeddings?
Got it. Thanks.
Yeah.
Okay. So we have a related question from Graph. So the question is, what's the intuition behind having Q, K, and V matrices? And related questions again from Hart. So could you explain how it takes KV from the encoder and Q from the decoder previous steps?
Yeah, so I can answer the first one. So the intuition, from what I understood, there was a they're kind of making an analogy to sort of what you see in databases where you have a query. Let's say you're going on Google and you're searching for something and you're matching that against some potential keys, which could be, for example, the title of the page or just specific keys of values, and then the values itself would actually be every entry that you're potentially matching against. Now, again, this seemed to be the high-level thing. I actually looked this specific question up when I was reading the paper. It kind of, once you actually consider the fact that the key and the value and ends up being similar kind of matrices, it kind of falls short at some point. It's an analogy that doesn't, at least in my head, doesn't hold with databases, but it is sort of taken from that world.
Okay. So then, can anyone answer
Yeah,
question
I
from
can take
Hart?
the second question.
Okay.
Yeah. So I'll just share my screen so that it is easier to explain.
Okay.
So I really like this blog. If anybody hasn't read it, please go and read it. The Illustrated Transformers. It has really nice illustration. So once we get the output from the encoder, what happens is the representation that we get, we transform them into different spaces like we do for self-attention, and we get key and value matrices. So these matrices are then used at each decoder step, and what happens with them is, so when they are doing this encoder decoder attention, the key and value will come from will be these matrices that we get from the final layer of the encoder, and just the queries will come from the previous this add and normalize representation. So they would again be transformed into some space. So like we do here, sorry, just a second. Like here for query, we are transforming them into some different space. So this would happen for these queries as well, and these keys we have already transformed into different spaces here. So I guess that answers the question.
Thank
Okay.
you.
Okay. So I also want to share animation. So because it's quite related to this question, uh, let me share my screen. So I already shared this GF picture earlier. So if you want to understand how that works, you can see at the encoding stage, what transformer does is it applies self-attention. When we are doing the encoding, every word can pay attention to any other words in the text. So it can aggregate their context into some more aggregated, contextualized representations, right? Then now we are going to the decoding stage. Then decoding can pay attention to both the input input sentences, input sequences, also the previous tokens in this sentence. Of course, it can pay attention to the later positions, but that's how the decoding stage works. Also, if you look at the paper in Transformer, here they have the description about the attention maximum in 3 different situations. So the first one is about the attention from encoder to decoder. That's after you have encoded something, then when you are decoding it, then the decoder can attend to the keys and values from the encoder, basically input sentence. So every position in the decoder can pay attention to the relevant parts in the input, so it can generate a decoded token. And then another part is in the encoder part. When we are doing the encoding, then here's we call it self-attention. Note that in the previous one we do not call it self-attention, but now we call it self-attention because we allow the encoder to pay attention to other positions in the encoder for aggregation. So all the keys, values, and queries, the Q, V, and the QK and V, they come from the previous layers of encoding. For example, in the first layer is word embedding, then we do self-attention, we get somehow more contextualized, transformed word embedding, and then we use them as a new Q, K, and V, and then we go on to get the final encoded self-attention word representations for the sentence. Similarly, for the decoder, we also do self-attention. In addition to the encoder part, the input sentence, we can also attend to the already decoded tokens. So that's why in the decoder, we also have this self-attention mechanism. Of course, one very important thing in the decoding is the masking mechanism, because we are not allowed to attend to the future positions in the decoding stage. For example, we are generating some text, you cannot pay attention to the previous to the future one. So that's why we use this masking out. So we can only attend to the already decoded position. So that's a very important paragraph for you to understand how the different attention mechanism works in this encoder and decoder mechanism. And also this GF, also the visualization in the presentation are also helpful. I also noticed a explanation from Srihari, I think is also very good. As he says, I have an interesting take on the intuition behind Q, K, and V. So we can think of the transformer as have an indexing scheme to find answers. So Q vectors are supposed to be asking the right question, and dot with K to give you a way to select your answers. That is V. I think that's also a very intuitive, very good explanation. Okay, so let's look at other questions in the chat. I think another question is from Srihari. What's the intuition behind having 8 of them? Is there some notion of each of them is learning different things?
Yeah, I mean, so I feel that is more of an empirical experiment that they tried. I mean, so I can see that why more than one heads would definitely help, because I mean each one of them could add different contexts. But I mean, as they have shown in the experiments as well, if they try to increase their heads to a very large value of, let's say, more than 16 or somewhere close to 32, the performance starts to go down. So yeah, I mean, so I feel that is sort of an
Okay.
Yeah.
empirical conclusion.
Okay.
Addition to Ayush's comments, so can I share the screen a little bit? So when you see model variation result, they just make it as the same with the h multiply dk same. So if they use their head 8, their number of dimension for the attention key is just 64. So I think as long as the memory works, I mean, they try to keep the computation same and they just do the experiment. And like as they increase the number of head, they should decrease the number of key, and then they lose the information from that. So it's like as the Ayush mentioned, it's like an empirical result for choosing the right number of the head.
Yeah, so in general, the number of heads is a hyperparameter in the design, depending on the computation resource you have, like the GPU memory.
Yeah.
Yeah. So another, maybe the final question, because we are running out of time. The final question from Wesley: what exactly constitutes attention? Is it just the idea of learning to scale vectors according to some input? Can anyone answer this question?
Yeah. So the way I thought about attention is, and this is actually why I did the whole thing of perfect latent space representation, is attention is just a process of finding sort of similar words or finding context within words by paying attention to other words. So I used the bank example, and then if bank knows that there's a river within the same sentence, then the context sort of changes. So attention really just becomes that mechanism. Now, what this paper does is it effectively, when you have that multi-headed attention, every single head has 3 linear layers for the query, key, and the values. And so, those linear layers, I represented them as matrices that get multiplied, but that's effectively the same idea as having linear layers. So what you're really training for is those 3 linear layers. The attention is just, so I guess the attention is just ends up being a condition that we want to maximize at some point. But the weights actually end up being the linear layers that are applied to the Q, the K, and the V matrices.
Okay. Yeah. I think that's a very good explanation.